Yeah, camps on everyone. Yeah, so this was the last thing that we did. Yeah, great. So let's go ahead. So assumptions of KTG. So this ideal gas equation, right, is derived under certain assumptions. The first assumption, the gas consists of large number of molecules which have negligible volume. So here the important thing, right, is this word, the large number of molecules. So when you say large number of molecules, we are talking in the order of Avogadro number, which is Na. This is how we give this. This is nothing but 6 into 10 bar 23. Learn that in chemistry. So when the sample is pretty large, what happens is we can assume the gas to be uniform. The gas can be assumed to be uniform or to be homogeneous. To be homogeneous. That is pressure, temperature, and density are same at every point. Now, this is important. For example, think of like this. Imagine in a container. So this is the kind of question they asked. Let's say in a container. Let me show you what they asked. Like something like this, they can frame a question. Let's say we got a container. Let's say which is 1 meter cube, and inside we have 10,000 molecules. Now, if the number of molecules are doubled, right? What happens to the pressure inside the gas? So we have a container with 10,000 molecules, and if the number of molecules are doubled, what happens to the pressure? Now, the thing is, ask yourself, first of all, a 1 meter cube, if you keep 10,000 molecules, it's like they're like so far apart and everything. Do you think if I take any small amount of space, you'll get same number of molecules inside? If you see, actually, most of the region will be empty space, isn't it? Molecules are so small, and 1 meter cube is so huge. They're almost negligible. So what happens is pressure and temperature are undefined. I'll tell you the meaning of it. See, for example, remember normally we say the density of population is 1,000 people per square kilometer. Ever heard this thing? The density of the population is 1,000 people per square kilometer. So the meaning of this is if you take 1 square kilometer, you can find 1,000 people. So if you go to the Sahara Desert and make 1 square kilometer, how many people will I find? You might not even find one, isn't it? So when you make this kind of a statement, what are you assuming? You're assuming the entire area is uniformly spread out, isn't it? We are taking an average. For example, if you take just Mumbai only, for every square kilometer, you'll find 1 lakh people. Mumbai has a huge density. Getting it? Same thing now. If you take the full Maharashtra, right? If you take the entire Maharashtra, suddenly this will drop to maybe like 300 or 400. But there are certain places in Maharashtra where if you go and actually take 1 square kilometer, you might not even find one person. So this statement, 1 lakh per square kilometer, is valid in Mumbai. Why? Because we are pretty sure the Mumbai population is so high for a given amount of city, right? It is uniformly spread out. But imagine in a city like Mumbai, if there are only 100 people, can I say every square kilometer there is one person? What if all the 100 people are just sitting in one room in a party? The rest of the city is empty. You're getting the point? So this statement, right? Actually, when we say 10,000 molecules, it's a pretty small number. So you can't define pressure. If the most of the space is empty, there is no pressure defined. There is no temperature defined. So literally, this equation which is there, PV is equal to nRT, is not valid. So this ideal gas equation is derived or valid when the sample is large. This is not valid. You can't use this. So if the number of molecules double, what happens? Nothing happens actually. The sample is too small in it for anything to happen. Pressure is still undefined. Since the number of molecules are very small, most of the space is empty. Look at this thing. I'm saying Avogadro number. We are talking about 10 power 23. If you have so many molecules in a given space, maybe in 1 meter cube, then you can say, it is little uniformly distributed. We call this thing law of large numbers. Ever heard about this? So what this thing says is, this actually kind of comes from statistics. When you have a large sample, things which are not supposed to happen will happen with higher frequency. For example, think of like this. Right now, in our class, right now, how many people are there with the name Arun? There, I am there, right? So there is one person, right? Now, if I ask you like this, how many people are there with the name Arun in entire Mumbai? Minimum. Did you see suddenly the sample size when I take a full city, right? Just give me a minute. So when you take a large, suddenly if you don't take Mumbai, right, there are thousands of Aruns. But what if you make a condition like this? What is the probability? Like, how many people are there with the name Arun, who is from Andhra, who teaches physics for 11th and 12th, who passed out from IIT Madras? Did you see? Suddenly, when I keep so many conditions, now, even if I take entire Mumbai, it still feels little difficult, right, to find one more. But what if you take the entire country? You might find another two or three. I know one person is in Pune, right? His name is Arun Kumar Sahu. He and I, we both studied in 11th and 12th, same college in Visakhapatnam. Then we both joined in IIT Madras. He is also electrical, I'm also electrical. His roll number is 5, my roll number is 6. So My full name goes like this, Arun Kumar Sana. His full name goes like Arun Kumar Sahu. So only these last two digits are different. H comes before N. So his roll number is 5. My roll number is 6. We both are physics teachers. He stays in Pune. You're getting it now. Suddenly, such a rare event, right? When you take all over India, you will find maybe one or two more. Suddenly, the probability bumps up. Getting it. So, when you have a large sample, right, things which were difficult to happen will happen with a higher probability. Same thing within the molecules. When you take, only like 10,000 molecules, there is no guarantee every space is same. But when you take one Avogadro number, now you can be sure there are so many molecules. Any given space will behave identically. Is it making sense? It's like in Mumbai, right? You go to any cow gully, it looks the same, chaotic and same. People are just running around and messed up. It looks identical. Maybe if it is a little more rush day, it might look more. But if you look to any local stations in Mumbai, right? If you see Thane, the other station, if you see the kind of crowd, the people, they look identical. They behave the same way because once the number of people in the station increases to 15, 20,000 at any point of time, they behave same. Clear? So there's a difference there. When I say this, law of large numbers, this thing happens a lot everywhere. Best example, look at your Uber and Ola. Now you might not know this guy, but 2000, you might be in school that time or even smaller. In 2015, 14 ka baat, now we are talking about that time, right? We didn't have Uber and Ola. So if you had to catch a flight at morning 3 o'clock, you know what we used to do? We used to go one day before to the auto stand, talk to the auto fellow, and tell him to come to by 2 o'clock or something. And he used to come and pick us up in the morning. We used to have something called Meru cabs, which always used to cancel exactly 15 minutes before the booking. Never worked. That was one of the most useless thing, Meru cab karke. So then, somewhere in 2015, 16, right, Uber Ola came. Now, when Uber and Ola came, they had a big problem. The customers used to say, boss, whenever we open the app, there is no cab. The cab drivers used to say, boss, there are no customers. You think it's a cyclical problem, right? The customers don't want to use Uber Ola because they don't find cab anytime. The drivers don't want to get into an Uber and Ola because there are no customers to book them. So what these people did, they said to the drivers, okay, if you make every day 7 rides, you can keep all the money, plus we will give you 2,000 rupees bonus per day. Yeah? But if you make 14 rides per day, you can keep all the money and you can keep 4,000 rupees extra. Nowadays, Uber, Ola, they take 25% of the total revenue they earn. So it was like you can keep all the money. Now imagine, look at the amount of money this. Even if this person earns only 200 rupees per ride, that goes to around 6,000 per day. In a month, that goes to around 1,80,000 to 2 lakhs. So drivers were earning roughly 1.5 to 2 lakhs every month. This was 2016, 17. We should check. If you see the news now, people are going crazy everywhere. Matlab, Bangalore mein situation was so horrible. They should send a cab to pick the software engineers, na? Infosys, TCS. The three software engineers together, their combined salary is less than the driver. So people used to get so pissed off. Many software people used to leave the jobs and become drivers. Now this something happened. When you're earning so much, what will happen? People want to become drivers, isn't it? Now it's a new profession. Becoming an Uber driver is the new goal in life. You get to earn 2 lakhs per month, right? And people were buying new cabs and everything. At one point of time in Mumbai, in entire, Mumbai Thane area, right? There were estimated more than 1 lakh cabs, meaning the number just went blasted. Now, when you have 1 lakh cabs, think about it. Tell me one thing. If you have only, let's say you're running an own company, right? And if you have only 100 cabs, if you have 100 cabs, where you want to keep these cabs in Mumbai? You want to keep them in Panvel, Dombivli? No one will come. Mostly you will run them in the western line, somewhere near Dadar, right? Andheri, that side, isn't it? But when you have 1 lakh cabs, what will you do? Can you keep 1 lakh cabs in Andheri and Dadar? Cabs will spread out, isn't it? That is what happened. Right now, even now, if you open your phone and see, you will find at least there are 10 cabs in your area. Forget about now. Night 3 o'clock, you open the phone and see, you'll find at least 4 to 5 cabs in your area. You getting the difference? So once we had 1 lakh plus cabs, now it has decreased to, I think it is around 40, 50 or 55,000. After that, Uber stopped, giving that extra bonus and all things became bad. But okay, that's a different story. Now, even now, if you see in the entire city, right, there are like 40, 50,000 cabs. There are enough cabs, so that is the reason at any point of time you will see at least the 10, 12 cabs. So law of large numbers. So when you have a large sample, right, getting a cab at any point of the day becomes obvious. Is there any time did you worry in the morning 3 o'clock, yaar cab milega, nahi milega? You don't worry now. Because it's like obvious, mil jayega morning 3 o'clock ko. But 10 years back, it was a nightmare. You had to go one day before and book an auto. And there is no guarantee that auto guy will come. And if it doesn't come morning 3 o'clock, you don't know how to go to the airport at morning 3 o'clock. There was no Uber, no Ola, no auto guy on the road. And then you're gone. It used to be like that. So remember this thing, law of large numbers, it's a very interesting thing. Based on that only, right, people also say there are so many planets in the universe. There is a high probability there is one more. You will find many civilizations like humans. That is again simply statistics. You have so many planets, it is tend to happen. So it goes like that. This law of large numbers, right, happens in business also a lot. For example, imagine you opened a small kirana stores. You go to the retailer and ask him, boss, give me 100 soaps. Then you ask him, boss, I'm buying 100 soaps. Now give me some discount. He says, ठीक है, 20 rupees ka soap, I'll give you for 18 rupees. So you come and sell this for 20 rupees and you make 2 rupees profit for soap. This is how a kirana stores work. Kidding it? But you know how DMart works? They go to the factory and they ask them, I want to buy 10 crore soaps. Right? How much will you give it for me? If you say, okay, I'll give you for 15 rupees, they'll say, okay, get lost. I'm going to another company. They say, ruko, 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 to 1 crore soaps, na? Now they will listen to what you're saying. He'll say, theek hai, I'll sell you for 12 rupees. He said, okay. Did you see the difference? And now what the DMart does something really interesting here. What DMart does, it's not greedy like other people. What it does, it sells you for 15 rupees. So when you buy outside, you get for 20. You're happy because you're getting for 5 rupees less. DMart is happy because it's making 3 rupees profit. The company is happy because they're selling 1 crore soaps. That's why next time when you go to DMart, observe, you'll always find the products cheaper than outside, isn't it? हर बार देखो, anything that you'll find 3, 4 rupees cheaper. And you'll not find every soap there. You'll not find every product there. You know why? If the company doesn't agree to give discount, DMart doesn't take. And DMart can give you so cheaply this soap is because it orders a huge number of soaps, and 1 crore soaps are nothing. You should see a DMart and see outside people how they're fighting and jumping. Right? Every day, one store will sell maybe like what 1,000, 2,000 soaps, and they have like 300 stores all over. They'll exhaust the entire supply in 6 months or 4 months. Again, it works. DMart can do this. Your local Kirana stores can't do. That's why no one can beat DMart so far. It becomes very difficult for someone to enter into the DMart. You and I, when we go to the shop, now maximum we buy 50 kgs rice bag. DMart goes and says, give me 50,000 tons of rice. And the best part, right, there is no one who can give him 50,000 tons of rice. You know what DMart does? He goes and he takes 3, 4,000 acres of land from farmers and says, these are the seeds, this is the product, you grow the rice for me. I'm going to come and buy in 3 months. So there. This thing is called economies of scale. So there, that's a law of large numbers, pretty useful, explains a lot of stuff, useful in business. When you are running one restaurant, it is fine, but when you're running 50 restaurants, you suddenly become profitable. So that goes like that. So keep that in mind. If you have a very small number of molecules, you can't use PV is equal to nRT. PV is equal to nRT is valid only for a large sample. The second thing, molecules are moving randomly. They do not have any preferred direction. That means if there are 10 molecules going in x-axis, you can be sure there are another 10 molecules going in y direction. So for a molecule, it has no preference x, y, z, anything is same. Motion is random. So if you look at the path of particle, it's completely random, and this gives you average displacement is zero. We discussed about this before also, Brownian motion. Therefore, the average velocity is also zero. So then we have a problem. That means if average velocity is zero, but does it mean the molecules are at rest? The molecules are moving, right? So there is an issue, like some molecules are moving, but you can't find anything. Then this person called Maxwell, he came up with a distribution. This is also another thing from statistics. We call it normal distribution. So Maxwell distribution of speeds. So what this thing says is, think of like this. If I take, your 11th standard, 12th standard ka CBSE ka marks from everyone. Let's say I think roughly around 5 to 6 people wrote the CBSE exam this year. So if I try to plot the marks, right, the number of students versus marks. Tell me one thing. How many, let's say highest is 100 and minimum is zero. How many people do you think will score zero? There might be, but few, right? How many people will score full? There will be, that also will be small. So if you try to plot them, you will realize again, when you're not talking only about Mumbai, if you take the overall, state, and if you try to put the marks, you will find a bulge like this. You will find most of the people, right, are in the ranges of 60s and 70 marks. There is a big range. This happens whenever the sample size is large. You will see it everywhere. Same thing happens in JE also. The highest is for 300 marks. You will notice there are very few people who got full marks, right? It's pretty rare someone got full marks in means. Once in a while it happens, right? You will find very few people in 250 plus, but around 140, 120, 150 range, there is a huge bulk of people, or even smaller actually, maybe around 70, 80 ka range, where there's a huge number of people. So this is what happens. Whenever you're taking any large sample, you will find people with very less scores are very small, high scores are also small. Most of the people are in the bulge. This is called a normal distribution. Why all that? Same thing. Look at the traffic. So on a highway, when you're looking at the speed of the cars, how many cars will go with the speed zero on the highway? One or zero, negligible. Maybe there's an accident, it stopped. How many cars go with the speed of 100, 120 kilometers per on the highway? Very few. There will be, but few. But how many cars will go the speed of 30s and 40s and 50s? You will see a bulge again. You're getting this? This bulge you will see everywhere. You will see this in the marks of the students. You will see in the traffic speeds. You will see this thing in the, the number of rich people with the money. How many people, like, in India or in the world, they earn like 1 crore every year? You will find them negligible. Like, you will find them maybe in thousands. How many people are there with the salaries of 20,000, 30,000, or 5,000, 10,000 per month? You will see the bulge again. This bulge you will see everywhere. Whenever there's a large sample, they tend to follow a normal distribution. But imagine on a highway, right? Early Sunday, early morning, there are only 10 cars. Do you think they'll follow this distribution? Road is so empty, all will go at 80 to 100 speed, isn't it? It doesn't follow normal distribution. So whenever you have a large sample, right, then you will get a normal distribution. Ha, Daksha, bolo now.
You assume that the direction is random for the
Yeah,
molecule. So, like, are we talking about the motion under some condition? Because, like, in
nothing. You just take, there's no condition. You just put a gas in a container and leave it. The molecules are just moving randomly.
so, so
You're
why is
putting
it?
gas in a container at rest.
Yeah.
You're putting gas in a container at rest. Bus.
So why is it an assumption that the motion will be like
They
will
don't
be
have any
random?
preferred direction. So that's an assumption, right? Who went inside and saw? You had to come up with some kind of an axiom or something. You're getting it. Again, see, molecules don't have preferred direction because there is a large sample. What if there is only one molecule inside the container? Now, do you really think it will not go only one direction? So that it goes only in one direction? Na? It has the preferred direction, isn't it? So when you have a large sample, you can assume it doesn't matter. All those things come from the first assumption only that the sample is large. So this thing, what I'm saying, a normal distribution, someone actually did this on CBSE ka, 10th standard marks from 2013 to 18, and they found something interesting. It didn't follow normal distribution properly. And that normal distribution, right, was going more towards 80s and 90s. And this guy found something more interesting. In 3 to 4 years of exams, no student scored 89, right? Technically speaking, all numbers must be equal, right? Students didn't score 34, 33. You know why? Whenever the student scored 89, they kept 1 mark and made him 90%. Whenever the student got 33, they added marks and they passed them. So this is one of the ways. So on an accounting, right, or something, if you're fudging numbers on an account, this is what they do. If the numbers don't follow proper random sequence normal distribution, we know you messed up the numbers. So works. So this Maxwell distribution, right? When you plot the speeds, this is how it looks. Again, remember, whatever I'm talking about, they all are kind of valid when the samples are large. If you talk about 10, 20 molecules, 10, 20 cars, this thing doesn't work. So we have NV subscript, and this is V. NV is nothing but dN by dV, that is number of molecules at a given speed. So if you plot the graph, it kind of looks like this. So here you'll see the bulge cut top. This is called V probable. I'll just write as VP. Then we have something called V mean. Then we have something called VRMS. What is the meaning of this graph? See, example, let's say if I take this point here, let's say this thing is 30, and let's say this is 20,000. The meaning of the statement is this: there are 20,000 molecules with a speed of 30 meters per second. You get the meaning of graph? For example, if this was 2 lakhs, there are 2 lakh molecules with a speed of, let's say, 60. So this graph gives you how many molecules are there at a given speed. So on the x-axis, you have the speed. In the vertical axis, you have the number of molecules at a given speed. Is this making sense? So that means most of the molecules ka speed, right? There are very few molecules with very high speed. There are very few molecules with very low speed. Most of them are in the bulge. This follows a normal distribution. That curve, we don't need it, right? And we don't need the derivation also, but that idea is important. So here, if you look at this curve, the area under this curve, which will be NV dV, this gives you the total number of molecules. VP is called most probable speed. This is given by root over 2RT by molecular weight. So the most probable speed is the speed possessed by the maximum number of molecules. So people came up with 3 different speeds. They had different purposes. This speed is more important in chemistry. Did you ever study this thing? When the reaction of ammonia is forming like nitrogen and hydrogen, the temperature should be some 500 degrees specifically. They write the temperature is very important. So the meaning of that is, think of like this: when the nitrogen molecule and the hydrogen molecule, when they collide at a particular speed of 300 meters per second, example, ammonia forms. If they collide with 400, ammonia won't form. If they collide with 200, ammonia won't form. So there is a perfect number for them to collide. Now you tell me, if you want to form ammonia, this speed should be what? Don't you want maximum number of molecules to have a speed of 300? That means V probable must be 300 for ammonia to form at a maximum rate, isn't it? Is that making sense? So when the maximum number of molecules possess the speed 300, there is a high chance of ammonia forming. So V probable is more important in chemistry. So the V probable helps you like that. So you need to mug up these formulas. That is your V probable. Have a look at this page. Clear? Next thing. What does V mean? V mean that itself says it is an average speed. V mean is the average speed of the molecules. This is given by root over 8 RT by pi m. Now, how did we calculate this? So if you have particles, let's say if you have only 10 or 20 particles, then the V mean is given by V1 plus V2 plus so on till Vn by 2. Sorry, Vn by n. For continuous distribution, I'll give an example of continuous distribution also. That means if I give you the normal distribution curve ka equation, which is actually in the form of e power minus x square something, the V mean is given by integral V dn by integral dn. This is V mean. Remember, this formula is valid for Maxwell distribution. If you change the function, this won't be valid anymore. Eight RT by pi m. Now, VRMS is something interesting. So what is RMS? VRMS, if you see, is root mean square speed. This is given by 3RT by M. So what this thing tells you is this talks about, or this gives energy of the system. Meaning, suppose if you have molecules going with V1, V2, V3, and so on till Vn. So what we are suggesting is, what if I can replace all these molecules with one single speed? Suppose if all the molecules will go with one simple speed VRMS, 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 I should get the same amount of energy. So kinetic energy of the system is half m v1 square, half m v2 square, so on till half m vn square. So you want to replace this with one single term, which is half. So you want to, this is the total energy of the system. So you want to replace this with half n m vrms square. Let me write it here. Half n m vrms square. This would be half m sigma vi square. Mm will cancel. We will get vrms is equal to root over sigma vi square by n. Look at the formula. Root mean square, meaning velocity ka square, uska mean and uska root. That now name itself will tell you what you're doing exactly. Again, remember, this is an important formula for Maxwell distribution. Let me write down this general formula also in the next page. It should definitely mug up this result. So V probable 2 RT by M, V mean 8 RT by pi m, VRM is 3 RT. Did you do this in chemistry? You must have seen something like this in chem. No. So for particles, VRMS is given by root over V1 square plus V2 square, so on till Vn square by n. For continuous distribution, VRMS will be root over integral dn v square dn by integral dn ka root. There, that's the formula for continuous distribution. Now, a few things, be careful here. That m in the formula which we are getting, V probable was 2RT by m. V mean is 8RT by pi m. T is the temperature in Kelvin. R is the gas constant, which is 8.3 joule per mole Kelvin. You can also write this thing as 25 by 3. That m is molecular weight in kgs, so be careful with that. It's not in grams. So these results are derived from Maxwell distribution. Let me show you a question that will make things more clear. But this is making sense. Why we need to define 3 velocities? V probable was useful for chemistry. More molecules possess V probable, the better the reaction. V mean is your average speed. That is the average distance they travel. VRMS was more important because it is talking about energy. So each speed has its respective purpose. We couldn't define everything with one speed because the molecules have so many different speeds. It didn't make sense. We can't get all the information with one speed. So we had to define 3 different speeds to talk about energy, the probable, and the mean. Clear? Let's see a question. So we have some particles. The speed of the molecules is given by 1, 1, 2, 2, 2, 2, 3, 3, 4, and 5. There are 10 molecules with the speeds of 1, 1, 2, 2, 2, 3, 4, 5. Find V probable, V mean, V RMS. Find V mean of oxygen at 300 Kelvin. If V RMS of helium is equal to V probable of hydrogen, find ratio of temperatures. By all 0. These are particles, na? This is not a Maxwell distribution. There are just 10 particles. For particles, we have a formula, na? So if you come and tell me, can I use 2RT by M? You can't use it, is wrong. Are you getting it? That was derived when the sample is huge. There are 10 molecules. So Maxwell distribution doesn't work only. So we have to use the regular particle ka formula and derive them. What is V probable here? You can see and tell. Look at the definition. The speed which occurs the maximum number of times. Which speed comes maximum number of times? 2 na? So V probable is 2. बस इतना ही करना था. Try, get them all. I'll give you 2-3 minutes. Right, Vihan. Let's see. So V probable is 2. What does V mean? Just add them up. 1 plus 1 plus 2 plus 2 plus 2 plus 2 plus 3 plus 3 plus 4 plus 5 by 10. How much is that? This is 10, 16, 4, 25, 2.5. What is VRMS? The root over 1 square is coming 2 times, so 2 into 1 square. 2 is coming 4 times, so 4 into 2 square. So it's 2 square, 2 square, 2 square, 4 times. 2 into 3 square plus 4 square plus 5 square and the whole thing by 10. How much is that? 2 into 1 square is 2. 2 square, 4, 4, 16. 3 square, 9, 2, 18. 16 and 25. 16, 16, 32. 18 to 20. 20, 45. 45, 32. 47, 77. That's root 7.7. Clear? You can leave it there. That is how you find in case someone gives you 4 or 5 molecules ka speed. Clear, everyone? So Maxwell distribution, all that formulas, all that assumption, nothing will work for 26A. But by definition, this is how you derive V probable, V mean, and VRMS. What about B? V mean, the formula is root over 8RT by pi m. 8, this is 25 by 3, temperature is 300 Kelvin. Pi is 22 by 7. Chalo, we'll leave it as pi. What is molecular weight? It is 32 grams per mole. So this is 32 into minus 10 power 3 kg per mole. There, that is the only thing. Be careful. Most people they write 32. It's not 32. It is 32 into 10 power minus 3. Because that is 32 grams per mole. Na? Gram is not an SI unit. Are you clear? That's it. Bika, that is the only reason to give that question. There's nothing there. Most common mistake, they write O2 as 16 or they'll write it as 32. You should not write that. You should write in kgs. So be careful with that. What about this guy? VRMS of helium. Helium RMS is 3. R, temperature of helium. Molecular weight is 4 into 10 power minus 3. V probable is 2. R, temperature of hydrogen. Molecular weight is 2 into 10 power minus 3. Open the square. Denominator में 10 power 3 minus 3 goes off. So this is 3 times temperature of helium by 4. 2 will cancel. This is temperature of hydrogen. So temperature of helium by temperature of hydrogen is 4:3. Easy. So these are some, easy level. This is that you'll get these type of questions also you will find. Any doubts on this? Then next one. Let me show you a little better one. This would be an advanced question. So this is your NV versus V. It's an hypothetical graph. This is a parabola. So this is an hypothetical distribution of speeds. This is a given, it is a parabola. And the maximum speed is V naught. So you don't have any molecule with a speed greater than V naught. So the speed distribution of molecules versus V is shown. So dn nv is nothing but dn by dv. That is the number of molecules per given speed. Total number of molecules is n naught. So all the molecules are n naught. So the question is find V probable, find VRMS. Now, in case you don't know what is a parabola, this is the general equation of a parabola, everyone, which is a quadratic equation. Now, exam they won't tell you this, so they'll expect you'll know this, but for now I'm giving it. It is in the form of y is equal to ax square plus bx plus c. This is the general equation. So in our question, it would be like this. dn by dv will be a into v square plus b into v plus c. So somehow you need to find a and b, isn't it? If I find a, b, c, won't I get the equation? First, you need to find the equation. So this much information you have. Total number of molecules is n naught, maximum speed is v naught, starting from 0. Using all this data, you need to find this equation. dn by dv is av square plus bv plus c. You need to find a, b, c ka constants. How do you find? Get that. First, find the equation. This would be an advanced, more than one choice question. So that red line is a parabola whose equation will look like this. dn by dv is av square plus bv plus c. What is a, what is b, and what is c? If you can find them, you know the equation. Once you know the equation, then you can use VRMS ka this general formula. Integral v square dn by integral dn and solve. I'll write that also in case you forgot. There, this is what I mean by continuous distribution. They'll not give you some velocities, they'll give you the curve and they'll expect you to solve. It's more of a max problem than physics. Think, give it a try for the equation. I'll give you a minute for the equation, then I'll show you the equation. V probable is the easiest one to find. Symmetry, na? Center point is the maximum, isn't it? V naught by 2 is V probable. That you can see and tell. show you the equation. See. So I know this is a parabola. So the general equation was this: dn by dv is av square plus bv plus c. So initially when v is 0, what is dn by dv? That is also 0, right? So this will be a into 0 square plus b into 0 plus c is equal to 0. C is equal to 0. There, c का value आ गया. You just have to substitute there. When v is equal to v naught, then dn by dv is again 0. That means a into v naught square plus b into v naught, c is 0 is 0. Therefore, av naught plus b is equal to 0. That is one more relation we have. Where do we get the next relation from? Area under the curve. The area under the curve, which is integral nv dv, which you actually see, this is nothing but total number of molecules, dn by dv into dv. Integral dn, which is total number of molecules. Which is given as n naught. So there, that is a third one. The total number of molecules is n naught. So that area under the curve is n naught. So how do you find area under the curve? So area under the curve will be integral. The function is av square plus bv. C is 0 anyway into dv. 0 to v naught must be equal to n naught. Is that making sense? We already proved C is 0. Square this thing. How much is this? This is av naught cubed by 3 plus bv naught square by 2 is equal to n naught. And from here, I already got av naught plus b is equal to 0. Take this from here and substitute here. How much will this be? I will substitute b ka value there. So this would be av naught cubed by 3 plus b ka value is minus av naught. So minus av naught into v naught square by 2 is equal to n naught. That will be v naught cube, v naught cube. That will be minus av naught cube by 6. There. So a ka value is minus 6 n naught by v naught cube. A का value आ गया. If I got A का value, I'll get B also. How much is that? B is minus AB naught. So 6n naught by V square. I got A का value, B का value, and C का value. Check the equation what it. Like I said, it's pure max. There is nothing there. The area under the curve is this, so integral must be n naught. V0 to 0, V naught 0 to 0. So three equations, three variables. We figure out the equation. This is what happens when you have a distribution. So they will normally, if they give you the equation, your life would be easy. And we use v naught and 0 as the roots and get the equation. Problem क्या है ना? You'll find infinite parabolas.
So, yes, sir, I got it. The coefficient will not be fixed.
You can get infinite parabolas with two roots. I need a third one to fix up the parabola. That is actually the number of molecules. The area under the curve is fixed now. You can't mess up that. Is this clear, everyone? So the equation is this. So we proved dn by dv is equal to minus 6n naught by v naught cube into v square plus 6n naught by v naught square into v. You can just take out that 6n naught by v naught square common. You end up by v square by v naught plus v. There, that's your velocity as a equation function of v. Now using this equation, can you find VRMS? What is VRMS? Integral v square dn by integral dn So what is dn? Send dv that side and integrate. Try, I'll give you a minute. I know dn by dv. So from here, get dn, send dv that side. Now take that and substitute here and integrate. And limits will go from 0 to v naught and 0 to, that is n naught anyway, denominator. Shouldn't it be a minus sign in the bracket? Yes. That's a minus sign. So getting the equation is one part. Now using this equation to find VRMS is the second part. It's a little tough one and it's a lengthy one. Hope everyone was clear. How did you figure out the equation? V naught. That means you're saying the highest speed is the RMS speed. So all the molecules possess V naught speed. Let me show you the each integration. So integral dn is fine. That is n naught only. That is the total number of molecules. So there's no need to derive the denominator. Numerator, integral v square. What is dn? Dn will be minus 6n naught by v naught square into v square by v naught minus v into dv. Six n naught by v naught square is constant. Let's push that out. Then you end up with v power 4 by v naught dv minus v cube dv. Limits will go from 0 to v naught. Minus 6n naught by v naught square. This guy will be v naught power 5 by 5 v naught minus v naught power 4 by 4. So 1 v naught will cancel here. That is 1 by 5 minus 1 by 4. That is 1 by 20. So we'll get 6n naught by v naught square into v naught power 4 by 20. V naught square will cancel off. That would be 3 n naught v naught square by 10. That is your numerator. So there, substitute here. So this will be root over 3 n naught v naught square by 10. Denominator is n naught. That will cancel. V naught into root 3 by 10. That's your VRMS, everyone. Right with this. Clear with this? Is this making sense, everyone? So if I give an equation, we can figure out from there. So if I had given you this equation directly, it would have been easy. Finding the equation was a big mess. And V probable would be the midpoint. That is a maximum. V probable is V naught by 2. That is the peak value. So at midpoint, we get max. It's a parabola, so midpoint will be maximum. Normal distribution is not a parabola. That is like this. So that won't come in the midpoint there. Clear, everyone? This is how they can frame advanced question. This would be an advanced one. More of a max. All clear with the equation part? How did I figure it out? Area, initial condition, V naught condition. So from there I get 3 variables. Once I got the equation, it is just a matter of putting it in the VRMS there and deriving it. Clear, na, everyone? Devansh, clear? Arnav, Soham, Sharman, got this? Ansh, clear? Puroja, Ishana, Niharika, Daksha, clear? Next one. Going ahead, Abhinav. So this is the second point there. So we have few more statements or assumptions there. Collision between molecules is perfectly elastic. Between molecules and container of the walls is perfectly elastic. There is no interaction between the molecules. Now, this is important. In ideal gas, we assume there is no interaction between the molecules. Normally, what happens, right, when there are two molecules, there's something called van der Waals forces. So the molecules do get attracted a bit, right, if they're little far. So we are assuming such kind of van der Waals forces don't exist. So except during collision, only when they collide, there is some kind of repulsion. They'll go away from each other, but we don't assume there is any other kind of interaction. So this leads to a very important point. So if there is no interaction between the molecules, that means the gas molecules will never form a liquid. So ideal gases cannot be liquefied. So how do you make something into a liquid? You are making the molecules get closer and the interactions become stronger and they form a closer bond forming liquid. Now, if you are saying there is no interaction between the molecules, no matter what you do, you cannot liquefy the liquids. Ideal gases cannot be liquefied. Ideal gases can be liquefied. So that is a consequence of the third point. If you don't interact, you can't become a liquid. Molecules obey laws of motion. That collision, change in momentum, force, it works. All that stuff works. And they have a negligible effect on gravity. Now, technically speaking, they are affected by gravity. Think about it. Imagine gravity is not there on the Earth. What would have happened? The atmosphere would have gone out, isn't it? The atmosphere pressure we feel is because of gravity. But for this to be experienced, right, you need to have a huge layer of gas. Like if you take in your room, right, the gas molecules are rarely affected. So we can ignore the effect of gravity if you're only talking about the size of like 2 to 3 meters per room or 10 meters per room, it doesn't matter. When you take 10, 20 kilometers of air, it's a different story. These molecules move in straight lines until collision happens. So because of the collisions, they start going random. But if there are no collisions, they'll just keep going in a straight line without any interference. And time interval between collisions is small. So these are the 5 things which are reasonable assumptions. So from here we get one more point. So tell me one thing: if a real gas wants to behave like an ideal gas, option question was like this: a real gas behaves like an ideal gas when option 1, high pressure, high temperature; low pressure, low temperature; high pressure, low temperature; low pressure, high temperature. There's a 4 options. A real gas behaves like an ideal gas when high temperature, high pressure; low temperature, low pressure; or what? Ask yourself like this. First thing, if you have high pressure, means what? The molecules are pushed closer. If molecules are pushed closer, won't they interact? So in an ideal gas, do they interact? So you don't want them to interact. That means you want to keep them as far as possible. Right? A real gas is an ideal gas at low pressure. You want to keep the molecules as far as possible. At high pressure, they get closer and they start interacting. And again, you tell me, when two molecules are passing side by side, do you want to, interact them for more time or less time? You want to keep the time as less as possible. So do you want to go them then? Should they go faster or slower? They should go fast, isn't it? If the molecules go very fast, they do not interact with each other. They don't get enough time to interact and high temperature. It's a good theoretical question. So if you have a low pressure and a high temperature, a real gas would be behaving closer to an ideal gas. Clear with this? So there are a few statements there. Next thing. So now if you take an ideal gas and a real gas, now in an ideal gas, the potential energy between the molecules is 0. Why? Potential energy is nothing but interaction between molecules. And you said in an ideal gas, there is no interaction. Since interaction between molecules is 0, there is no potential energy. So therefore, when you say what is the energy of the gas, so whenever you say internal energy, it has actually 2 components. It has kinetic energy, the kinetic energy of the molecules, plus potential energy, which will be 0. That means the internal energy of the gas is only kinetic energy. So in an ideal gas, the total energy of the system is only because of the kinetic energy. There is no interaction between the energy. This cannot be liquefied. And the equation is PV is equal to nRT. That's your ideal gas equation. We study only ideal gas. Real gas we don't have in our portion, but you should have an idea about it. You can get theoretical questions. So if you take a real gas, potential energy is not 0 because molecules interact. Now, there is something interesting there. If the pressure is very high, tell me one thing, at very high pressure, what will happen? Molecules are pushed towards each other. If the molecules are too close, what happens? This is the first thing we studied in thermal expansion. If you bring the molecules too close, what will happen? They will repel, isn't it? So if you bring the molecules very close at high pressure, potential energy is positive. At low pressures, the molecules are little far, the potential energy is negative. So potential energy, right there, it depends on whether you're pressure is less or more. These can be liquefied. Basically, there can be a phase change. And the ideal gas equation is given by P plus AN square by V square into B minus NB is equal to nRT. Seen this thing in chemistry? This is a real gas equation. Now in this, the Eka value, right, this will tell you about the interaction between molecules. So that component takes care of interaction between molecules. It affects the pressure. And this V takes care of the volume of the molecules. Remember what is V actually? V is the volume in which the molecules can freely move. So NB is the total volume of the molecules. So the total volume of the container minus volume of the molecules, you're free to move in that space. So in an ideal gas, B is 0 because volume is negligible. A is 0 because there is no interaction. So when A and B becomes 0, it becomes an ideal gas. Volume and pressure corrections. That only, na? So this is that takes care of interaction between molecules. So that affects your pressure. This affects your volume. The fundamental reason is that. Clear? That is one. The next thing, degrees of freedom. This, we had a glimpse of it in rotational mechanics. The symbol is F. It is the number of independent ways a system can possess energy. Energy or motion. Then we have the second one. It's called law of equipartition of energy. Now, what this law says is whatever energy you have, right, that should be equally divided among different degrees of freedom. For example, let's say you're there and your younger sister or younger brother is there who is in 8th standard. Not too small, but decent kid. And you are there. If your mom brings 10 chocolates, right, you're in 11th standard. Now your mom gives this logic. Because your brother is elder or your sister is elder in 11th standard, they should get 7 chocolates and you should get 3 chocolates because you're younger. What happens? There will be a war. Getting it? So the same thing. So law of equipartition of energy says it doesn't matter whether he is smaller or bigger, everyone gets equal share. Getting it? So something nature also does the same thing. Even if you have 5 degrees of freedom, whatever energy I have, I will divide equally among the 5 degrees of freedom. Getting it? Everyone gets an equal share. In case you don't believe me, try that once and see what happens. Until unless your sibling is too small to understand, or maybe it is something which they don't like, it's a different story. So energy associated with each degree of freedom is equal to half kT for molecules. So here K is the Boltzmann constant. K is actually given by R by Na. R is your gas constant. Na is your Avogadro number, 6 into 10 power 23. So when you actually substitute the values, 8.3 by 6 into 10 power 23, this turns out to be around 1.38 into 10 power minus 23. That's the value of the Boltzmann constant K. Small n is the number of moles. Capital N is number of molecules. So number of molecules are given by number of moles into Avogadro number. One mole contains one Avogadro number of molecules. Have a look at this. I'll put it down in more detail in the next page. So what is the kinetic energy of a molecule? So kinetic energy of one molecule is given by F is the degrees of freedom, and each degree of freedom will have kT. The F by 2 kT. The kinetic energy of a gas. Now a gas contains a lot of molecules. So that will be total number of molecules into kinetic energy of each molecule, which is N into Na, F by 2 kT. But I know Na into K becomes N. So this is F by 2 nRT. That's the kinetic energy of the gas. Be careful. If you're talking only about one molecule, N won't matter. If you're talking about the gas, number of moles will matter. And the total energy or the internal energy of the gas, just now I showed, it is equal to the kinetic energy of the gas. Internal energy is kinetic energy plus potential energy. This term is 0. So the energy of a gas is same as the kinetic energy of the gas, F by 2 nRT. There, these are the three important ones. Basically, this is the beginning of thermodynamics. We are slowly entering thermodynamics actually and directly. Clear? Now, let's see what is this F ka value. Now, if you take monatomic, example, monatomic is like a single molecule. Example, helium, argon. These things will have, it can go in Vx, it can go in Vy, it can go in Vz. So it will have three translations. And technically speaking, if you see, the molecule can also rotate about this axis. There should be one rotation also, but we said in an ideal gas, size of the molecules is negligible. If size of the molecules tends to 0, the moment of inertia 2 by 5 mr square will also tend to 0. Therefore, the rotational kinetic energy, which is r phi omega square, will also tend to 0. Make sense? So technically for a monatomic, there is also one rotation, but we ignore that because the size of the molecules is 0. So there, for monatomic gases, the degrees of freedom F is 3. It has only 3 translations and no rotation. If we talk about diatomic, same thing, you can go Vx, Vy, Vz. You can rotate like this. You can rotate like this. You can rotate like this. Again, same story. If the axis is passing through the molecules, this is negligible. So these two are counted because see, this is a finite distance. So we have 2 rotation and 3 translation. So for diatomic, F is 5 at low temperature. This is also same for CO2. So even though CO2 is triatomic, if you look at carbon dioxide, it's the molecular structure it behaves like diatomic. CO2 also has F is equal to 5 because that structure, right, it can't rotate in any other plane. It's a linear molecule. So linear triatomic molecules are similar to diatomic. Also F is equal to 5. But if you take something like H2O, right, or ozone, then it's a different thing. They can rotate like this. They can rotate, in multiple axes. It will get different. I'll show you how to get all those things. So it's a diatomic at low temperatures. But if you increase the temperature, something else happens. The molecule starts vibrating. High temperatures, molecules vibrate. So if you have a molecule, this kind of behaves like a block and a spring. These are called vibrational modes. And in each vibrational mode, you will have vibrational kinetic energy. It's like a spring, right? So there is a potential energy and there is a motion. So in each vibrational mode, there are 2 degrees of freedom. So if you have F vibrational modes, let me write it as N. If you have N vibrational modes, this will give you 2N extra degrees of freedom. 2N vibrational degrees. Example, they asked a question like this. They said a polyatomic. Now, polyatomic, I will tell you, I'll give you the table. A polyatomic molecule has 2 vibrational modes. Now see, in a polyatomic, right, we have 3 translation, X, Y, Z, that is okay. We have 3 rotation. So polyatomic has 3 rotations plus 2 into n vibrational mode. So in this case, it is 2 into 2. So total here F is 10. Clear this? So at high temperatures, the molecules will start vibrating. You have to include this vibrational degrees of freedom also. So this is the table which you need to. That's it. The question which I gave you, that is the main thing. If you remember that, it is sufficient. But let me give you the table. Exam, they actually asked you gamma. So here now the thing is that F actually gets confusing. So let me just change that. So let this be n vibrational mode. So this is 2n degrees of freedom. So this is actually 2n by 2. So the 2 cancels out. We'll end up with n, 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 and n. So what they did, right? Each vibrational mode has 2 vibrational degrees of freedom. So they actually wrote 2 into half kBt. 2 got cancelled, so you got kBt. You're getting the thing? So basically, each vibrational mode will have 2 into vibrational degrees. That will be half into kBt. So that is kBt. Because you're already using F ka symbol, na, they're also using F there, so it gets confusing. So this is 2 degrees of freedom actually. This is 2. So this guy actually becomes 2 into half kBt. There it is fine. You need to mug up this thing. Monatomic is clear. Therefore, see, monatomic F is 3, diatomic F is 5, triatomic non-linear, no vibration F is 6, diatomic with one vibration mode F is 7. There are 2 vibrational degrees and 2 rotation and this thing. Triatomic with n vibrational mode F will be 6 plus 2n, where n is the vibrational mode. So if there is n modes, so 2 modes, so then it will be 6 plus 4. Clear, everyone? You should definitely mug up the result. This was a question in the exam. A triatomic molecule has 2 vibrational degrees of mode, find gamma. What is gamma, CV, CP? We will see in thermodynamics. Clear, everyone? Take a break. Come back by 7:11. There's a bit of a theory, so just go through them. Any doubt so far? Come back in 10 minutes. Yeah, comes on everyone. So suppose if there is a mixture of gases, how do you find the average degrees of freedom? So F average is given by N1 F1 plus N2 F2 by N1 plus N2. Example, if you have 2 moles of helium mixed with 1 mole of hydrogen. So here the F average will be 2, helium is only 3 monatomic, and hydrogen is 2. Assuming low temperature, it is 5 by 2 plus 1. That is 6 plus 5, 11 by 3. Same thing, if you also look at the equation, PV is equal to nRT, we can do something here. Multiply and divide by 3 by 2 and 2 by 3. This will be 3 by 2 nRT. Now, if you remember this, kinetic energy of the gas is F by 2 nRT. This is total. But if you get only translation component, that will become 3 by 2 nRT, isn't it? Because there are only 3 degrees of freedom, right? There is a kinetic energy of a molecule is F by 2 kT. Kinetic energy of a translation of a molecule is 3 by 2 kT. So the moment you say translation, there are only 3 components, F won't come. So this can be written as PV is equal to 2 by 3 kinetic energy of translation. Do you remember from the beginning I was telling you statement, temperature depends on random translational kinetic energy. So that means rotation, right? No matter how much it rotates, it will never create any temperature. Only the translation component is responsible for temperature. So temperature depends only on translational kinetic energy. So that is a bit of a theory about degrees of freedom, law of equipartition of energy, kinetic energy of molecule, gases. Have a look at this. Let's see a question. Let's see some theoretical questions based on this. Any doubt so far? Let's say we have 2 containers. We have N1 moles of helium, N2 moles of oxygen. You gave them same heat. Both the containers, you have given them same amount of energy. Find the ratio of kinetic energy of helium by kinetic energy of oxygen So if I simply say kinetic energy of helium, I'm asking about total kinetic energy of the gas. Translational kinetic energy of helium by translational kinetic energy of oxygen. Temperature of helium by temperature of oxygen. Get them. Let's see. What's the first answer? C. Just now we said, whatever energy you're giving, the kinetic energy of the gas, or you can say like this thing, whatever heat that you give is going where? Whatever heat you're giving, that is going into kinetic energy plus potential energy, the total energy, but potential energy is zero. So heat is equal to kinetic energy. So 1:1, right? Think of like this. In one classroom, there are 10 students. In another classroom, there are 100 students. I gave them 100 chocolates in every classroom. How many chocolates did I give to each classroom? 100, right? Why do I care? How did you distribute them? The question was, what is the kinetic energy of the gas? Whatever heat I gave, that became kinetic energy. So both the systems have same kinetic energy, isn't it? Is that making sense, everyone? Whatever energy is given, that becomes the kinetic energy. There is no potential energy there. So all the energy is kinetic energy and they're equal. What happens is this. The helium, what it does, now for helium, F is equal to 3. So whatever energy you give will distribute only among 3 people, Q by 3, Q by 3, and Q by 3. So basically it's all translation. Whereas if you look at oxygen, it has 5 degrees of freedom. So it will share among 5 people, Q by 5, Q by 5, Q by 5, Q by 5, and Q by 5. In this, 3 components are translation and 2 rotation. That is the difference. They'll have same amount of energy, but how they distribute will be different. So for the second question, kinetic energy of helium, this will be Q only, whereas this is 3Q by 5. That is 5:3. Nothing is mentioned, always take low temperature. They will specifically mention if it is high temperature. Right? Whenever they have now degrees of freedom, they will tell you it's a high temperature. What about temperature of helium? So kinetic energy is nothing but F by 2 and RT, which is equal to Q. So temperature is proportional to 1 by NF because Q is same for both. So this is number of molecules of helium, degrees of freedom of helium, number of molecules of oxygen, degrees of freedom of oxygen. This guy will be N2, 5 N2 by 3 N1. There. Check your answers, everyone. In O2, sorry, 2 rotation. Is this making sense, everyone? This is how they'll frame questions theoretically. Both the gases have same amount of energy, isn't it? 1:1. What they do is different. They will distribute in a different way. So in this, 3/5 of the energy goes for translation in oxygen. Any doubts on this? So temperatures will be different because translation is the only one responsible for temperature. Rotation don't create any temperature. Clear with this? Let's see one more like this. Daksha, clear with this? Sure. Vignajit, Ojas, Soham. Let's see similar one. I'll just change a small thing. Again, we have N1 moles helium, N2 moles oxygen. This time they have same temperature. So find kinetic energy of helium by kinetic energy of oxygen. Find kinetic energy of helium molecule by kinetic energy of oxygen molecule. So they'll mention if it is molecule. If they don't mention, they're talking about the full gas. Translational kinetic energy of helium molecule by translational kinetic energy of oxygen molecule. Now get them. You're getting the previous question, same heat is given. Here, same temperature is given, so they can play around. What is the first one? So kinetic energy of a gas is F by 2 nRT. You said temperature is same, so this is proportional to F is to N. So this guy is N1, 3 N1 by 5 N2. Make sense? For the second one, you are saying for kinetic energy of a molecule. So kinetic energy of a molecule is F by 2 kT. Number of moles won't come, so it is proportional to only degrees of freedom. 3:5. Now, if you talk about translational kinetic energy of a molecule, now it has only 3 degrees of freedom. That is only 3 by 2 kT, which is constant. 1:1. That means at a given temperature, no matter which kind of molecule you take, translation energy will be same. Is this making sense, everyone? Easy questions, but you should know the theoretical part. Just try to be careful there. Clear, na, Devansh? Arya? Clear with this? Ahana, got this? Clear? Let's see one more. We have a container. They're insulated. Insulated meaning heat can't come in, heat can't go out. So in the middle, you have a tap. So you can open this tap to connect them in this thing. So here the pressure is P1, volume V1, temperature T1, it's a helium gas. Here pressure is P2, volume V2, temperature T2, it is a hydrogen gas. Find the final pressure and temperature when the tap is opened. So when you open the tap, gases get mixed up. Find the final temperature and pressure. When tap is opened. Hope the question was clear. How do we figure out? Like I keep saying, the first important thing is always draw the final state. If you know how your final state looks, things would fall in place. So when you draw your final state, you'll ask yourself a few questions. Okay, how does the pressure look like? How does the temperature look like? And then you will see something. So when you take this, what do you think will be the pressure? Will it be different or same? It has to be same. Why? If the pressure is different, gas will keep flowing till the pressure is same, no? What about the temperature? Same or different? Same. If the temperature is different, heat will flow till the temperature becomes same. Does that make sense? The whole thing becomes identical. So basically the pressure and temperature must be same in both the containers. Now what remains same in this thing? In this entire process of mixing, what remains same? Number of moles. Moles can't change, no? So here how many moles are there? N1 will be P1 V1 by RT1. Here the number of moles is N2 P2 V2 by RT2. Here I can use my ideal gas equation P dash V1 plus V2 total volume, total number of moles N1 plus N2 into RT1. There, but I got two variables P dash and T dash. Where do we get the second one from? What else can I do? I conserved moles. I can conserve something else. The container is insulated, meaning what? Heat can't come in, heat can't go out. So what is constant? Total energy. We can conserve energy. So energy conservation. So what is your initial energy? F helium by 2 N1 R T1 plus F hydrogen by 2. So this is the energy of the gas N2 R T2. This is F helium by 2 N1 R T dash plus F hydrogen by 2 N2 R T dash. Substitute the values. 2 will go off, R goes off. This would be 3 N1 T1 plus 5 N2 T2 is equal to 3 N1 plus 5 N2 T dash. There. So you got the temperature from here. 3 N1 T1, 5 N2 T2 by 3 N1 plus 5 N2. Once you got T dash, substitute, you'll get P dash also. Yeah, you can substitute N1 and N2 to get the answers. Clear, everyone? So those are the two things. Conservation of moles. Basically, you conserved mass. Moles is nothing but mass. You did conservation of mass and you did conservation of energy, which you actually see they're fundamental conservations. So they're not really new kind of conservations. The only thing is for energy, we need to take the energy of a gas, which is F by 2 nRT. All clear with this? Going ahead. Sharman, Devika, clear? Arnav, Arush, Chainil, clear? Pratik, next one. Next one. Ansh. We have a container with a piston. We have a spring also. This is vacuum. So you have a very small gap here. That is also vacuum. Initially, system is at rest. Then what you did, remember, this is still vacuum. You injected some gas into this gap. So you introduce some gas in here at temperature T0. So when you put gas inside, what will happen? It will push the piston up now. Height went to h. Gas is introduced and the height goes to h. Spring constant we don't know, mass of the piston we don't know. Then what you did, you doubled the temperature. So keeping the gas same, the temperature is doubled. And you observe the piston goes even higher. Obviously, if you have more temperature, you have more pressure. So the same gas, but you made the pressure temperature double. And the height became h dash. The question is, if temperature of the gas is doubled, so you know already h ka value. So when you introduce a gas at temperature T0, you got height h. If temperature is doubled, find h dash. Piston moves up. To h dash from h. Is the scenario clear, everyone? So initially you took a container, complete vacuum. You had one piston, it is hanging with a spring. Now when you introduce some gas at the bottom, it pushed the piston up. You got height h. Now keeping the gas quantity same, you double the temperature by heating it, and the pressure will increase because more temperature. It will push the piston more. It went to h dash. So find h dash in terms of h. No, spring constant is not given. Nothing is given. Only this information we have. Let's see. See, one thing is clear. The moment you realize the gas is pushing the piston, you're talking about forces. And when you talk about forces, we draw FPDs. So let this pressure be here, P1. Let the pressure here be P2. Okay. So initially, when you draw this FBD, let the spring be elongated by X. I don't know how much is X. This is mg. Since it is in equilibrium, Kx is equal to mg. Now in the second case, when the piston has gone up, what do you think happened? What happened to the spring elongation? Decreased, right? So it becomes K into X minus H, agreed? Right, Purvaja. And mass is mg. And now the gas is also pushing up. So this is P1 into area. So K into X minus H plus P1A. Now these two are balancing mg. Kx and mg will cancel. You will get P1A is equal to KH. This is equation 2. Now if you take the next situation, now the spring gone even further. So this is X minus H dash, your own weight mg, and this is P2A. This would be Kx minus H dash plus P2A is mg. This will be P2 into A is equal to KH dash. Now in all this thing, the gas, what remained constant? The number of moles. So N is equal to, N into R is equal to P1 V1 by T1 is equal to P2 V2 by T2. So initial pressure is P1, volume is A into H, temperature is T0, final pressure is P2, area into H dash by 2 T0. But what is P1? K into H. So this will be K H square by T0. This is K H dash square by 2 T0. K cancels, T0 will cancel. So we'll get H dash is equal to root 2H. Make sense? See where it went wrong. There, I did nothing. We just used an ideal gas equation. Number of moles are same. So P1 V1 by T1 is P2 V2 by T2. And we used equilibrium. Every time it goes up, the sprinkler compression is decreasing. Elongation is decreasing. So this is how they'll frame questions on this. Check it out. They're not tough, but the thing, you should have seen these kind of questions and you should think like, FBD to draw karna hai, because the moment you talk about a spring, there's nothing we can do. You have to draw an FBD. And I said that is at rest, so you're talking about equilibrium. Clear, everyone? Any doubts on the steps? Arush, clear? Devansh? Let's see one more. Mhm. This is a question from Erido. The language can be a little weird. Read the whole question once. Why will piston ka mass change because you're introducing gas revoges? What are you talking? Why will the piston ka mass change because you are introducing gas at the bottom?
So no, I mean to say, do we always assume that it will have mass?
It didn't matter in the question.
Yes, but okay.
Nothing is mentioned, you assume. They will normally tell you massless piston. See, the thing is, if they didn't mention, so better you to take, right? That is a more ideal case. And even then, answer doesn't change, means you're safe, isn't it? But technically, if they didn't mention, that means the answer would come same even if you take and if you don't take. It shouldn't have mattered that way. Read the question, then I'll explain you, then I'll give you more time to tell you. Now see. So did you get the question? So we have a vessel like this, which is smooth. Inside you kept two pistons. This area is A1. They didn't give. This area is A2. This also is not given. But what is given is the difference in area. He says the cross-sectional area of the upper piston is delta S greater than the lower piston. So what he gave is A1 minus A2 is delta S. You're getting it? He didn't give A1, he didn't give A2, but he gave the difference is delta S. Similarly, he didn't give you mass, but he said the mass of the two pistons is 5 kg. So that is M1, this is M2, total mass is 5 kg. In the middle, you have a string. That means both the pistons will either go together up or come down together up. Getting it? They can't be separated. Now the question is saying by how many Kelvin the temperature must change so that this whole system will move 5 centimeters. Means I want this setup to go 5 centimeter here like this. You're getting how it is? If you want this setup to go 5 centimeters up, then what should be the temperature? Question is clear, everyone. If it goes up, will the volume increase or decrease? Volume will change, na? Dekho na. If it goes up, this is the extra volume. This will go up, this will decrease. So it has increased more than decreased, na? Volume is increasing. Because the upper one has more area. If it goes up, there will be more volume increase than volume decrease. So that you can keep the distance between them constant. Or else it will stretch so it will get messed up, right? See, I can be sure na, if this travels X, this also will travel X. That's it. There's nothing there. If you tie them with a string, they have to travel same distances. Think I'll give you 2 minutes. Start with an FBD. They have given mass, pressure. They're saying it is an equilibrium. That itself should give you a big idea. Both forces are involved. Let's see. First, let's draw the free body diagram. This is there, this is the thread, and this is there. What are the forces? So from outside, we have P naught into A1, P naught into A2. From inside, we have P gas into A1, P gas into A2. And you have your own weight, mg. Tension is there, but that is internal. Clear with this? Now, if you look at this, interestingly, you'll find something, see. P gas into A1 minus A2 minus P naught, that will be equibalancing P naught into A1 minus A2 plus mg. So pressure of the gas is P naught plus mg, A1 minus A2 is delta S. And did you notice something? This is constant. Meaning no matter how much this piston goes up and down, pressure can't change. P naught is constant, mg is constant, delta S is constant. This is an isobaric process. So even when you increase the temperature, to keep the pressure constant, volume will increase. That is the first part you need to figure out, that the pressure is constant no matter if this goes up and down. See now, did this matter in this FBD? Did it matter how much it went up and down? The equations won't change. So pressure of the gas will always remain constant no matter how much ever this goes up. That is the first conclusion. Then, now if it is isobaric process, I know PV is equal to nRT if I differentiate on both sides. Then I have P dV plus V dP is equal to nR dt. Now, since it is isobaric, this term will be 0. So from here, we got P into delta V is equal to nR into delta T. So pressure into change in volume will give you nR into change in temperature. There, I'm getting my delta T there. Now look at this diagram here. Now what happened? The piston went up. By how much? It went up by 5 centimeter. So let's call it some L. Meaning, see, from this position, this went up by L up. So from this position, it went up by L. So how much volume did it increase? So this is the volume of increase. How much it increased? A1 into L. This is the decrease. How much it decreased? A2 into L. So what is the change in volume? So delta V, change in volume, is increase minus decrease, which is A1 minus A2 into L, which is delta S into L. There I got my delta V. You're done. So change in temperature delta T is P delta V by NR. P is the pressure of the gas, so P naught plus mg by delta S. Delta V is delta S into L by NR. You know all the values, substitute, you'll get the answer. I know P naught, I know mg, I know delta S, I know NR. Check out the steps. So the main thing is that figuring out that it's an isobaric process, and then you'll get P delta V is NR delta T. So when it moves up by distance L, you have to find the change in volume. It's a good one, meaning it would take time if you try to do this thing. But these are the kind of questions you'll get. Mechanics plus the ideal gas equation. They're not going to just ask you gas equations like your chemistry. Check it out. Any step you're not convinced, please ask me. So the important thing is we proved even if it goes up, the equations won't change. Clear, everyone? Next thing. Mean free path. These are some important questions which are popping up every year in mains. So you should know the results. Results are more important. So what is the mean free path? It is the average distance traveled by molecules between two consecutive collisions. Like we said, molecules collide, so but they will travel some distance before colliding. So this is given by lambda is 1 by root 2 pi sigma square NV. Sigma is your molecular diameter. You should write down this formula. We are going to need this. You need to remember the formula. We don't have the derivation for this. NV is nothing but number of molecules by volume. This is called number density. Meaning there have been questions which are like direct straightforward. CET method directly they ask which of the following is the free mean path. You know the formula, you take it and come. Now, if you have free mean path, you can find time also. So we define something called relaxation time. Symbol is tau. This is the average time interval between two collisions. How do we get that? Simple. Time is nothing but distance by speed, which speed means speed. So this formula becomes 1 by root 2 pi sigma square eta v into v mean. And what is v mean? 8 RT by pi m. This is the second important one. So if actually you know free mean path, you'll get everything from there. So from here, we also define something called as collision rate. Z, this is the number of collisions per second. So if the time interval between two collisions is tau, then the number of collisions per second is 1 by tau, which is root 2 pi sigma square NV V min. So you're just playing around with this. Have a look at this. You should know these results. First time we saw these kind of questions, I think was in 2017 or 18. First time they started popping up. We didn't understand what the hell were this but when we went to the NCERT and started searching, we actually found this formula in some corner. Everyone copied the formulas? Put it up, put on the formulas. We're going to need them now. Let me show you a few questions on this. Going ahead. This was a PYQ. This is how they frame questions. Consider an ideal gas in isolated chamber as the gas undergoes an adiabatic expansion. Do you guys know what is adiabatic process? I'll be teaching you later on, but for now, just remember this. In adiabatic process, TeV power gamma minus 1 is constant. You should know this relation. Temperature and volume ka relation, gamma is called adiabatic constant. Don't worry about it. We'll see that later on. Now they're asking, find the average time of collision between molecules is proportional to volume power Q. So he's asking, what is Q? Get this? And D is not the answer. So just to give you the formula, tau is 1 by root 2 pi sigma square NV V mean. There. So you know this equation, you know this equation, you know ideal gas equation. Using this all this information, find that tau is proportional to V power Q, find Q. Try, I'll give you a minute. Let me show you one. So what is NV? Number of molecules by volume. What does V mean? 8 RT by pi m. So there. So tau is proportional to volume will go up by root T. There. So tau is proportional to V by root T. But T is what? TV per gamma minus 1 is constant. And then T is proportional to 1 by V power gamma minus 1. So this is V by root over 1 by V power gamma minus 1. So tau is proportional to V power 1 into V power gamma minus 1 by 2. A power m into A power n, A power m plus n. So V power gamma plus 1 by 2. Clear what we did? So basically NV may we have number of molecules by volume. There is one volume sitting inside. V mean may 8 RT by m. There is a temperature inside. So convert the temperature into volume. So you'll get everything in volume. There, that is how we do these kind of questions. Play with this. Let's see one more like this. Any doubts on this? So yeah, adiabatic process, you should know this thing. I'll be teaching in demo. For now, take that. Get this thing. I think this is 2019, I guess, or 23. Similar question. An ideal gas is enclosed in a cylinder at pressure. Now they're talking about pressures and temperature 300. The mean time is this. If the pressure is doubled, temperature is 500, you find the new mean time. So again, time is nothing but 1 by root 2 pi sigma square eta v v mean. Try, I'll give you a minute. So you need to get this tau in terms of pressure and temperature now. So you always need to see what is being changed. So get that in that terms and then finish it off. Again, same story. Just now we proved that tau is proportional to volume by root T, right? We just now got it in the previous one. Now from ideal gas equation, PV is equal to nRT. So you don't want volume anywhere. So V is proportional to T by P. Substitute here. So tau is proportional to T by P root T. The root T by P. That's what you have to do. Every time you have to get it in terms of what is being asked. So tau 1 by tau 2 will be root over T1 by P1, P2 by T2. So tau 1 is 6 into 10 power minus 8. T1 is 300. P1 is 2 ATM. You said it became double, so 4, and this is root 500. So we have tau 2 will be, 2 will cancel, 3 into 10 power 8 into root over 5 by 3. Yeah, this is approximately 4 into 10 power 8. There's only two options with 10 power minus 8, and the 4 is only this one. Clear with this? So it's always the same thing. That same formula will keep coming. You just need to convert it and finish it off. So in the previous question, we messed up volumes. Here we messed up pressure and temperature. There is volume and temperature. Clear with this? Let's see one last one. This is a good one actually. Now they give two different gases, argon and xenon, 40, 131, same temperature, have same number density, meaning NB is same. Diameters are given. Find the ratio of mean free time. Again, the same formula, 1 by root 2 pi sigma square NB V mean. Let's get this. This is a good one. There is a small trap. Finish off. Last one for the day. Yeah, diameters in meters. SI units, no? Always. The catch here is this tau is proportional to root 2 is constant, pi is constant, NV is constant, and they also give same temperature. So this is the mistake people do. Temperature is same, so V mean is same. So this is 1 by sigma square. This is 8 RT. ये same था, but denominator में there is a molecular weight. Molecular weight is not same. Are you getting the catch? Most people forget that molecular weight. Everyone will see temperature is same, so speed is same. They forget that M is different. So this is proportional to molecular weight by sigma square. Ka root. That was a trap. So there is a molecular weight sitting inside that V mean that messes up the thing. So now if you write tau 1 by tau 2, so molecular weight tau of argon by tau of xenon, argon would be 40 by 131, diameter would be 0.10 square by 0.07 square. That is roughly 4 by 13, and this is 100 by 49. That's close to 2 into root 4 by 3 or 4 by root 13. Now, one thing I'm pretty sure, this is definitely less than 2, but slightly greater than 1, right? There's only one option. Now, for people who forgot the molecular weight, they will get an answer as how much? They'll get the answer as some 2 point something. So most people will mark this and come. Clear? So this is approximately 1 point something. That is only one which is closest to 1. See, root 16 is 4, na? That would have become 1. So root 13 is slightly less than 4. So it is slightly greater than 1, but it is not 2. Clear with this, everyone? There. So that is about KTG. After the class, I'll be sending a sheet also to solve. So in that you have questions from thermal expansion, calorimetry, KTG, everything is there. You can do that. So next class, when we catch up next week, we'll start off with heat and thermodynamics. That's quite an important chapter. Thermodynamics and heat transfer. They in entire heat and thermo, those two are the main weightage ones. But these chapters are the base. Okay. So with that, we'll wrap up for the day. Right. We'll catch up again next week on Tuesday at 5:40. So any doubts, anything you can stay back and ask. Also free to leave. Do remember there's an exam online. The deadline is tomorrow. So do make sure to give it. So any doubts, anything, stay back and ask. Also free to leave. So first you can ask me anything in the class notes and then
Thank you, sir.
1 sec.